70 years ago, we found the key to the solar system. It would unlock affordable launches of thousands of tons at a time, rapid travel to all the planets and even beyond the solar system. But we decided not to use it. Nuclear energy. This isn't science fiction. Legitimate, feasible designs were tested and presented by scientists involved in the Manhattan Project in 1946. Their work had started in secret and first revealed to the world as a tool of terrifying destruction. Now they were eager to show off its peaceful purposes. Their plans would solve one of the greatest problems facing the rocket industry, the rocket equation. The equation that demanded chemical rockets to become massive stacks of fuel with huge, expensive sections being discarded into the sea. Nuclear energy could solve a lot of this problem, but not through nuclear reactors providing thermal power to exhaust gases. This would be like drinking from a swimming pool through a straw. Efficient, but without the thrust needed to get large payloads off the ground. The world had witnessed the immense power nuclear bombs could deliver in an instant, equivalent to tens of thousands of tons of chemical fuel in a much smaller package. If these explosions could be harnessed for a rocket, they would transform how we got to space. But the only way to get a vehicle moving with nuclear explosions was to place it inside the fireball of an atom bomb. Most people today would assume everything is simply destroyed inside the hellfire and leave the insane idea at that. Scientists in the 50s had a different approach. This is how Project Orion was born, and this is its story. The first question the engineers and scientists behind Project Orion had to answer was, what can survive a nuclear blast? The U.S. military was very interested in this question. They needed to know how to build shelters to resist a nuclear attack and, in turn, how powerful their warheads needed to be to destroy hardened targets. The heat, radiation, and shock wave from a detonating nuke could destroy the other nukes in a volley too. So knowing how closely they could be spaced was vital. Answers would come from the many nuclear tests they were eagerly conducting, specifically the experiments that involved placing different materials at varying distances from ground zero of a nuclear device. One such experiment involved Lou Allen's balls. Lou Allen was an Air Force physicist who was worried about America's supply of tritium, a heavy isotope of hydrogen, necessary to fill thermonuclear warheads. The first fusion bomb was detonated in 1952's Ivy Mike test, and it was quickly followed by plans for warheads of much larger yields into the megatons, which needed more tritium. Allen knew lithium could transform into tritium after being bombarded by neutrons and the radiation of a uranium fission bomb could do the job. So he had these balls blasted by a 20 cotton yield device to test that theory. Experiment Viper took 1 meter wide steel spheres filled with a lithium-containing material and placed them just 10 meters from the point of detonation of an atom bomb. The spheres would absorb the intense radiation without being destroyed thanks to a graphite coating. Graphite was used because it has the highest vaporization energy for its weight of any solid material, allowing it to absorb a huge amount of heat energy before becoming a gas, which is why it is so commonly used in a blade of heat shields. But two surprising discoveries were made as a direct result of these experiments. First, they discovered that when the balls were engulfed by the thermal blast of the warheads, a millimeter-thick layer of graphite vaporized into a protective gas shield, allowing the spheres to withstand a 150,000-degree fireball without damage. And second, the spheres had been shot out of the fireball like cannonballs by the expansion of that gas. What if this phenomenon could be harnessed for a rocket? The idea didn't get much traction. That was until Sputnik sailed over the United States in 1957, kicking off the space race. Vast resources were quickly unlocked to fund efforts that would beat the Soviets in space now and in the future, including less certain technologies with great promise. The Advanced Research Projects Agency was set up in early 1956, and Project Orion began under the same year. Papers detailing the physics of the principle became workable designs, and larger concept spaceships began to be planned. But Project Orion wasn't just sketches. Actual designs began to be tested, including a small rocket that was pushed to 100 meters in altitude by 6 explosive blasts. Another was a scale model that was exposed to repeated shock tests. Several spaceship designs of various sizes and purposes were drawn up, ranging from lunar Orions that went to the moon to 10,000-ton Orion ultra-heavy lift vehicles that carry their own weight into orbit with each launch. Each one would be a massive step ahead of the spacecraft of their time and still remain unmatched to this day, capable of crossing the entire solar system in a month or heading to Alpha Centauri in a human lifetime. But for the sake of this video, we will focus on one specific design, the 4,000-ton Orion ship, the first serious proposal from the project. It was to be a heavy lifter, a 78 meters tall bullet able to deliver 1,115 tons into low Earth orbit, but also capable of delivering 300 tons to Mars and returning without refueling. Docking in space had not yet been attempted, so being able to send up whole space stations in one piece or perform entire missions with one vehicle was a distinct advantage. Declassified reports tell us how it would have worked, focusing on 4 critical elements. The first and most important element is the nuclear devices that would propel the spaceship. It couldn't be just any design. It had to be both small and powerful. Both the United States and the Soviet Union were trying to compete by building the biggest and most powerful weapons possible. But scaling up nuclear bombs is easy. Trying to make them work effectively at a small scale is much more difficult. Neutrons are needed to sustain a nuclear chain reaction, but they are highly penetrating and quickly leak out of an atom bomb. Smaller cores let go of more neutrons, so fewer fission reactions happen inside and much of its fuel is wasted. But this can be compensated for with higher explosive compression to increase density and thereby increasing the chances of neutron collisions. But that comes with its own design challenges. The US was obsessed with inventing miniature warheads to fit on a new generation of submarine-launched ballistic missiles to arm a new branch of the United States nuclear arsenal. The key was plutonium, a more volatile fuel than uranium encased in beryllium that efficiently recycled and reflected neutrons. This was even used to create the Davy Crockett tactical nuke designed to be launched by soldiers on the battlefield. This approach was perfectly suited to Project Orion's needs, and they quickly adapted the idea into the miniaturized nuclear bombs that would be lobbed behind the rocket, and they dubbed them pulse units. These pulse units would weigh about 1 ton each and release 25,000 tons worth of TNT. Half of the pulse unit mass, however, was a plate of tungsten. That plate was the difference between a bomb and a rocket engine. We know that nuclear bombs create intensely hot fireballs that rise off the ground as menacing mushroom clouds. But the actual output of a fission reaction is lots of X-rays, fast-moving neutrons, and a thin burst of plasma. Earth's atmosphere absorbs them within a few meters and turns them into heat. That's how the mushroom cloud is formed as the heat rises and cools. In a vacuum, an atom bomb just looks like a flashbulb burning out. A mere spark followed by an invisible wave of radiation. still deadly but useless for moving things in space. A thick plate is added to the pulse unit to intercept the energy of the fission reaction, absorb it as heat, and explode out as a rush of hypervelocity gases.